Let's talk about feature extraction in computer vision. So first we'll see how we understand one image or how computer understands one image. So if you see one car or a dog, how your brain identifies or distinguishes the car from the dog. So humans use years of experience. If we see something with ears, fur, legs, tail and a specific shape, we can tell that this is a dog. If something is having wheels, headlights or windows of specific shape and all, right, then we'll say that this is a car. We humans also use context, like headlights on a road means that's probably a car, but a similar light inside a room may not be a car. If something is barking in a park, so then it's probably maybe a dog. So the context also helps disambiguate visual information. But how can a machine identify or a model can identify an image? So machines doesn't see the objects, right? So they just see numbers. So for an image, it will see the pixel intensity values. So how an image is represented? So an image is represented as a grid of pixels, like a matrix. So it will have pixels and each pixel stores a numerical value. So the grid will have some height and width, right? It will be like a matrix and it will have the pixel values. So in grayscale image, each pixel has one value representing the intensity from darker to brighter. So 0 means it's a black, 255 means white. So from 0 to 255 we'll get different shades of, like from black to white, different shades of gray. So if it is a colored image, then each pixel will have 3 values for red, green and blue. And it's represented as 3 stacked matrix like this. So here also each pixel value will have will determine the intensity of the pixel. So if we have a dog image, so we'll have a red channel, green channel and blue channel separately, and each will give the pixel intensity values. So the raw image contains the shape, right, color, age, texture, background noise and all, right? So our model, our computer, if you are training a computer to see the image, they don't need everything. It depends on the task, right? So if you want to classify an image, we don't need always need the color and all. Often shape and ages are enough to distinguish objects. So here we have, let's say this is a grayscale image and we have the pixel intensities in grayscale, and it is enough to tell that for a computer that this is a dog image. So shape and edges are often enough to distinguish objects, and this edges like highlights the structure. So if we have this car and dog image, and if we just extract the shape and shapes or edges, right, we'll get something like this. And this is enough for a computer to tell this is a car and this is a dog. So other extra features, color and all this, we can ignore. So only the important features for a particular task will be extracting, and in most of the cases for images, these shapes or edges, these are enough. So for most of the feature extraction cases, we convert the RGB image into a grayscale image, as color is not often important. If there is any problem, if there is any computer vision task we are performing where color or other features are important, we'll extract those features based on that. So now there are few old feature extraction techniques in computer vision that we used to use earlier. So those are designed by humans and it's based on the domain knowledge. Two popular methods we have, like HOG or HOG. This is histogram of oriented gradients. SHIFT, this is scale invariant feature transforms. So we'll see quickly like the basic intuition behind this manual feature extraction techniques. Just the basic idea we'll see to build some intuition. So what happens here? So let's say this is the pixel values I have taken for a from a small part of an image. What this hog will do, it will calculate gradients or small change in the x and y direction for each pixel in the image. So consider this pixel. For this pixel, we'll compute the gradients, the change in the x direction and in the y direction. Gradient or change in the x direction, how we'll get that? We'll subtract the value on the left from the pixel value on the right. We'll take the value on the left, we'll subtract it from the value on the right. Gradient or change in the y direction, how we'll get? We'll subtract from the value above from the pixel value below. So we'll subtract this one from this one. So this gradient magnitude, it will be higher when there is a sharp change in intensity and such as around the edges. So you see here this pixel. So left side we have 13. This is a darker value, like darker pixel. 223, it's a very bright pixel, right? So from darker to brighter, this is intensity is changing rapidly, right? So that is what we are trying to calculate. So the gradient magnitude we are calculating, that will be higher when there is a sharp change in the intensity, and that means there will be some edges in this pixel is contributing to some edge. Now we calculated the changes in the x direction and in the y direction. Now we'll calculate the total gradient using the Pythagoras theorem. That is square root of gx square plus uy square. This is the total gradient. And also we calculate the direction of the gradient. So the direction is basically this angle theta. So tan theta is gy by gx. So theta will be arc tan gy by gx or tan inverse gy divided by gx. So we got the gradient magnitude that will define the intensity of the change and the angle direction of the change. And after we do this, we get an output like this. This is not the exact output. This is some assumptions. For this dog, we might get an output like this. So you see the gradient values we have here. It will define the intensity of the change and also the direction. And from this, if we just feed this gradient magnitude and directions, this informations to the computer, it's easy for the computer to get those numbers and predict that this is a number, this is a dog. Now this thing we did earlier, right? We calculated the change in the x direction and y direction. This can be seen as applying some filter. Now what is filter? So the concept of filter is, you see this matrix here, -1, 0, 1. If you take this part of the pixel and you overlap this with this, right? We just get the values like 13, 91 and 223. So then we'll take the element wise product. So we get -13, 0 plus 223. We'll take the sum of element wise products. It's the same as 223 minus 13. The same thing we did earlier. So we subtracted the left pixel value from the right pixel value. So we're just trying to formalize this. So this is one filter we have taken, and we'll overlap this with the pixel values. We'll take the element wise product and we'll take the sum of those products and we'll get the intensity changes. This is in the y direction. So in the y direction, if we just take this value, this pixel values, we'll get 30, 91 and 64. So the values will get minus 30 plus 64, same as 34 we got. So this will give the intensity changes in the y direction. So we will come up with different types of filters. That's what we used to do earlier for computer vision. Different types of filters we used to find out, and we used to find out different types of features from the image. So yeah, we saw earlier. So the same thing we are calculating from this, applying this filter. So here I have shown the same thing. This is the overlapped pixels. We'll apply this filter and element to product sum of this red region. It is effectively, it subtracts the value on the left from the pixel value on the right. And here also we're applying the filter here. It's effectively subtracting the value on above from the pixel below. Now we see different types of filters. So in most of the cases we use 3x3 filters or 5x5 filters depending on the task. 3x3 filter is very common. So let's say we have one small simple image here, and it has darker pixels here in the upper side and brighter pixels here. So that means we have one horizontal edge, right? And we'll see, we'll have this 3x3 filter. So we'll pass this filter is scrolling through this image. This filter is passing through this image, and then we'll calculate the element wise products. We'll sum those element wise products, and then we'll use that information to find out the age. So you see this 3x3 filters is just passing through this image. Now what we'll do here, we'll apply few filters. So there is a well-known filters called Sobel filters. We have two types of Sobel filters, like Sobel X filter and Sobel Y filter. Sobel X, it measures intensity change along the X direction. It detects vertical edge, and Sobel Y, it measures intensity change along the Y direction. It detects horizontal edge. So GX, so this is the Sobel X filter. You see, in this side, left side, we have negative values. In this side, we have positive values. We'll just place this filter onto the pixel images. That means what it says, right? We are subtracting the left side values from the right side values. So this is giving us the intensity change in the Y direction. So you see, you consider this 3 pixel, right? So if we have placed this, it's basically deciding if we have a vertical edges. So the intensity changes from the left side to the right side. If the intensity changes from the left side to the right side, that means we have a vertical edge, right? So if we are calculating changes in the X direction, then we'll detect a vertical edge. So with Y filter, it's basically, you see, where you have negative here and positive here. So that means we are detecting the intensity changes from above and below, right? So it will detect one horizontal edge. So which filter do we have to apply for this image? We have one horizontal edge, right? So we will apply it. So we'll Y filter, because it will find out the intensity change in the Y direction. So it will get the horizontal edge. So first, let's say the filter is here. So the filter is this, so we'll Y filter, and these are the pixel values. So if you just take the element wise product sum, you see, so you get 0 values basically. If we take the element wise product sum, we get 0. And one thing we can, this is the basic intuition, is if the pixel values are similar, so this element wise product sum will be closer to 0, very small. If the pixel values are different, that means there is some edge, so this element wise product sum will be high. So that we'll see here. So let's say the filter is here now. So this is the pixel values and this is the filter. So you see from the first row here we get minus 40. From second row is will give 0 always, and the third row is getting 200 plus 400 plus 200, so 800, right? So first row gave minus 40 and third row gave 800. So the value is 760. It's very high. That's because you see in this side we have darker and in this side we have brighter. So the intensity change is higher. It is much higher. So we got one horizontal edge. Similarly, when the filter will be here, right, or here, then also we'll get this higher value because first row will give minus 40 and third row will give 800. So we'll get a higher value. So what will get, our output will look something like this. So in this part you see 0 0 and 0 0. This part means the pixel values are similar, and here we see pixel value, this output is higher, right? So that means there are some edges. So this output, the filter output we got, so this can be negative or positive because we don't know which side we have brighter and which side we have darker. We are always taking the difference between from right to left, right, and from below to above, right? So that's how we are subtracting. So this can be negative or positive. And also this value, this pixel of the filter output, it can exceed the 0 to 255 range, pixel range, right? So these values, these are not actual pixel values. The 760 values we got, it represents the edge strength. The higher the value, the drastic the changes. So we saw earlier here, this values are 10 and this are 200. So the change is very high, right? This is higher, right? So that's why we got a higher value. So the value we get, it represents the edge strength. So what we usually take the absolute values because it doesn't matter which side we have darker, which side we have brighter. It's basically we found one edge, right? So we take the absolute values and we'll normalize the values to visualize. So basically in some way we'll be normalizing the values to get one output like this. So and this output we can visualize like this. So there we have found one edge. Similarly, let's say we have similar image of with a vertical edge. And this side, left side, we have darker image, darker pixel, and right side we have brighter pixel. And the 3x3 filter is passing through the image pixels. Now, what type of filter we need? So, well, X filter or Y filter. We are detecting vertical edge. That means we have to find out changes in the left, from the left and right? So changes in the X direction we have to find. So we need one Sobel X filter. So after applying Sobel X filter, we'll get some output like this, right? So it clearly shows this, there we'll get a vertical edge. So earlier we used to use this type of filters. We used to come up with this type of filters. We used to apply it to the image and we used to detect edges or shapes. Now how deep learning does this now? Deep learning learns these features in an image by applying learnable filters to the image through convolution layer. So we don't create those filters and apply those filters manually now in deep learning. What we do, we have some convolutional layer. So some extra layers in the deep learning network for feature extraction. So those are the convolutional layers. So this type of dense neural network we already have seen. So these layers are new extra now. So this is nothing but this will have the filters. So we'll just define the filter size. Let's say 3x3 filters, 5x5 filters and all. So this different filters will add. We can have multiple layers of filters. And earlier, if we and now we are having multiple filters, means we are extracting different types of features from the image. Now we are having multiple filters, multiple layers of filters maybe, so that we can extract different types of features from the image. We directly feed the image to the network, and what we do is, at first these filters, right, it will have the size, right, and it will have some random values. During training, they are updated using back propagation, so they become good at detecting useful visual patterns. So initially, when you are feeding some, when you are having some random values for the filters, so it might output something wrong, right? So we are passing one dog image, it might predict it as cat. So as we'll train the network, this filter will get the appropriate values so that it detects the image better. Now here we have some quick flow. So how it is done. So we'll have feature extraction layers with filters and dense neural network layers, like this dense layer will have, and these are the task specific ones, right, whether it's a classification one or object detection one or whatever, some other task with the image. So for that we'll have this dense layer and we'll have this feature extraction layers with filters. I'll pass this dog image right into this network. So we'll start with random filters with random weight values. So we'll have, let's say we'll decide multiple such 3 by 3 filters, and this will have random values. We'll feed an image and we'll do the forward pass. So, and model will output some prediction, right? And it's not necessarily correct as we have random filters, right? So the filters are not proper. So the model will output something rubbish, some wrong output maybe. We'll calculate loss or error, let's say cross entropy loss, with predicted cat and actual dog. So actual images of dog, right, and predicted class type is cat. So we'll calculate the loss. Then we'll do back propagation. Back propagation will compute how much each filter contributed to the error. That's what back propagation does, right? And it calculates the gradients, right? So also for the filter weights also it will calculate the gradients. Then we'll apply gradient descent to learn the filter weight values. So in each gradient descent iterations will update the weight values till we converge. So that's how we'll come up with different types of filters for different types of data set or different types of tasks. So what do these filters eventually learn? So this is our assumptions, and based on our experience with the model training, we can tell that early layers learn edges like vertical or horizontal edges, corners, simple textures. Middle layers can learn curves, patterns, shapes, like small eye, ear, will and all. Deeper layers will learn some semantic features like dog's face, car's wheel, eye shape and all. Like the deeper the network is or the better the architecture of the model is, the better it will learn to understand the image. Now this is some basic image to build some intuition. So we are feeding this dog image. So initial layers, the early layers might learn small edges, patterns and all. When it is the middle layers will learn small eyes, let's say nose, ears, legs and all this. The deeper layers will understand this is face, there is this body of the dog, and ultimately we'll find out that this is a dog. So instead of manually coding filters like Sovel, Hog, Shift, so we saw we had manual filters like -1, -2, -1, 0, 0, 0, 1, 2, 1. This type of manual filters earlier we had, right? So instead of that, deep learning discovers those filters by minimizing loss from the dataset while doing the training. So that is the advantage of the deep learning. We don't need to have extra feature extraction shapes. We can just feed the image to the network.